Hello again. So in the last video, we started talking about redshift, and we said that if a light that is moving away from us, then the light is shifted towards the red end of the spectrum, and if something's moving towards us, then the light is shifted towards the blue end of the spectrum, and this is all down to the Doppler effect. And we can actually quantify what redshift is by using this equation. So redshift, given by Z, is the observed wavelength, take away the wavelength at rest divided by the wavelength at rest. And by wavelength at rest, we mean one that's measured in a lab or measured on Earth without moving. And the observed wavelength is the one that's coming from something that is moving. So where lambda observed is the observed wavelength in meters, and lambda rest is the wavelength of the light if the observer and light source are not moving. As the wavelengths are all in meters, that means there's meters at the top, meters at the bottom. They cancel out, so Z has no units, so 0 units. So when a galaxy is moving away from us, the redshift should be positive. Because if you think about it, if a galaxy is moving away from us, the observed wavelength will be stretched out. Remember that slinky? Something's moving away from you, the wavelength is bigger. So bigger minus smaller divided by smaller gives you a positive. However, if it's moving towards you, the observed wavelength will actually be smaller than the rest wavelength. So it'll be smaller minus bigger, so it will give you a negative value. Okay, so you can tell by looking at the redshift value whether something's positive, whether it's positive or negative, whether it's moving away from us or towards us. And redshift can also be expressed, so there's two equations for redshift, as Z is V, which is the velocity of whatever's moving, divided by c, which is the speed of light, so 3 times 10 to the 8. Okay, so I'm going to go through an example of using redshift. So a spectral line for sodium usually appears at 589 nanometers. The corresponding spectral line for sodium observed in a star, so that's a moving one, is observed to be 598 nanometers. First of all, A, is the star moving towards or away from the observer? So again, you want to think about that slinky. Okay, so we said that when it's at rest, when it's on Earth, it's 589 nanometers. Okay, and when it's observed, when it's moving, it's bigger, it's 598. So if the wavelength is bigger, think about the slinky. Is it coming towards you or is it moving away from you? It should be moving away from you. Okay, so the wavelength at rest is 589 nanometers. The observed wavelength from the thing that's moving is 598 nanometers. So the observed wavelength is bigger than the wavelength at rest. So it's moving away. Okay. B. What is the redshift for this star? Okay, so we know two equations for redshift. We've got the two above here. So observed minus rest wavelength divided by rest wavelength, or V over C. Since we haven't been given any speeds, we're going to use the top one. So redshift is observed wavelength minus rest wavelength divided by rest wavelength. So you put those numbers in. So observed wavelength is the one that from the moving star for 598. The rest wavelength is the one that's measured in the lab or one that's from stationary observations. So 598, take away 589, divided by 589. And if you put that into your calculator, it comes out to be a positive, which is good, 0.015. The reason I put positive in there is just to show that we know that positive means it's moving away. So we were right in part A. Part C, what is the speed of the star relative to the observer? So now we know the redshift, we can then use this equation. So the redshift is 0.015. Speed is what we want to find out, and the speed of light is 3 times 10 to the 8. So the speed is going to be 0.015 times 3 times 10 to the 8, which comes to 4.6 if you put it into your calculator, times 10 to the 6 meters per second. Okay, so that's an example of how to use those equations. So now I'm going to get you guys to do some questions